Now we're going to look at an application of a binary search tree. So this is from an actual homework assignment that I once gave. The assignment is to write a program that reads a file, stores the words from that file in a binary search tree, and then prints words that match certain criteria from the tree. So in terms of the specific requirements, the program receives the file name on the command line, and the syntax would be something like this. The name of your executable, which here I'm calling my program, the name of the file to read from, and so it's the words from this file that we're storing in the binary search tree. And then the third thing here is the term that's used to indicate which words should be printed, and I'll discuss that here in a moment. The file is to be read exactly once, so each word in the file needs to be extracted and stored in our binary search tree, and then we also need to maintain a count of how many times that word occurs in the file. When storing the words, we want to allocate just enough space to store that word. So that's something we need to consider when we create our structure definition. Now in terms of the words, one of the things we need to consider is what's really a token or a word in this case. So let's say we have space, the word book, followed by another space. Well, if I'm using a space as a delimiter, that's clearly a word. But if I have space, book, comma, space, and I'm only using spaces as delimiters, well, then that makes book, comma appear to be a separate token. Well, I want those to be treated as the same token and the count for book to be updated to 2 in that case. So what we're going to treat as valid characters in a word will be lowercase letters of the alphabet, uppercase letters of the alphabet, and digit characters. So it would be possible to have something like this, listen to me, count as a word. Also, I don't want uppercase and lowercase versions of words to be treated as separate tokens. So all the words need to be converted to lowercase. And that also means we need to deal with characters that aren't in this range, lowercase letters, uppercase letters, or digit characters. So question marks or commas or semicolons or other non-alphanumeric characters need to be dealt with. After storing the words from the file in our binary tree, as well as their counts, we want to print all words that are equal to or greater than the term that was passed in here. So what I mean by that would be if rabbit actually occurred in the document, and rabbit is the term that I provide here, you should print rabbit and its count, as well as every word that would come after rabbit if we were to sort the words. If rabbit's not there, then it's just every word that would come after rabbit in terms of sorting. So what do we know about the data and can use in our logic? Because there's always something you have to hard code. You can't make a program completely general, but we want to minimize the hard coding. So what we know is that tokens can be delimited by a space, assuming that we've dealt with this right here, that only alphanumeric characters constitute a token. And the number of tokens per line can vary, but we do know that a line can be stored in 1,000 bytes. So we don't want to hard code anything else. And then ultimately we want to free whatever memory is dynamically allocated. So let's look and see what we're dealing with. So I happen to give this file the Gettysburg Address, but it should work on other things. So we notice we have a mixture of case here, here's a space, here's a period. So if the word equal shows up multiple times, I'd want all the versions of equal to be treated as the same word. Here's liberty with a comma, so I need to deal with the comma. Some other places have commas. Here's some dashes, things like that. I want to deal with all those, so that way I'm just dealing with what normally is considered a word. So let's see, at least in part, what we're talking about here. So if I have something like this, cat, dog, bat, dog, horse, cat, dog. Now we could maintain a list, right? We could have the word, the count, and you could say, okay, I have cat, I've seen it once, dog, I've seen it once, bat, I've seen it once, dog is right here. So I want to update the count to 2. Horse, seen it the first time. Cat, okay, update the count to 2. Dog, update the count to 3. Right? Well, part of the requirements were that I store these things, so I care about efficiency of finding the terms to update. As this is written here, when I saw dog the second time, how do I find dog? Well, probably what I do is just start at the top of the list and work my way down. But there's no structure to this that makes it easy to quickly find something. So it's basically search, and in worst case, you'd have to make it all the way to the bottom of the list. So you might have to look at every term here to realize that, say if the next thing was giraffe, I'd have to go down the entire list and say, oh, well, giraffe is new. Or giraffe, sorry. And add it there. So if there were a lot of words, we would like to have a more efficient way to search and find out if something's already on the list or not on the list. That's one consideration. Another thing is, in terms of the output, and I don't think I mentioned this looking at the requirements, but we want to print in sorted order. So I want to print these out as, bat 1, cat 2, dog 3, actually giraffe now, and horse. Assuming that the word I passed in was less than or equal to bat, then I'd get all these. So we need to consider this. So if I just have a list, these things aren't really dealt with, and so I could deal with it by, say, sorting this. That's obviously the way to deal with the sort order. Sorting would also help with the efficiency if I had an existing sort order, but I don't have that here. So this is one of the reasons why I want to use a binary search tree. Now, of course, the homework explicitly said you had to do that, but even if it didn't, this would be a good choice, especially if we have some reasonable amount of balance built in. Now, for my implementation, I'm not going to deal with the balance case, but if I were constructing this, I'd have something that looks like this. So we have cat, then I see dog, then we get bat, then I get, in this case, actually I see horse first, then giraffe, something that looks like that. So there's some reasonable amount of balance. Hopefully it doesn't become too skewed, because if it does, then I basically am back to the issue over here, other than the fact that because of the binary search tree, the terms are still at least sorted. It's just that this part wouldn't really be in effect if all the terms are basically going in this direction. So this is one reason why we're using a binary search tree. So now let's look and see what my actual implementation is. So I have a lot of functions. Let's start with the structure definition. I said that I only want to allocate enough memory to store the particular word. So it's right here, I'm creating a char star. So what would be the alternative to that? Well, if I'd done something like this, I could certainly say struct node char word, say 20, and then the other things, right? I could do this, but there's a couple issues here. One is I have to know that every word can be stored in 20 bytes or less. And of course, this really means 19 characters as we normally count them, because I need room for the terminating null. But if a lot of the words are less than this, I'm wasting space. But what if I don't know in advance what the max word can be? Well, then I have to take some guess and hope it's reasonable. And if I'm wrong, then I can't really fix it. So by changing this to this, then when I get a word, I can use string length. say if I'm given cat, this will return 3, but I need room for the terminate null, so I add 1 to that, and this all is in my malloc call. And then I take this and attach it to this. So I have exactly the amount of space I need for this. Now what's the issue with this approach? Well, I still have to allocate memory, which means there's some performance requirement here, but that's probably not that big a deal. But then I also have to keep in mind that I use malloc here to create the node, which means I need to free that memory eventually. But since I'm using malloc also here, I also need to free that. So here's a call to malloc, here's a call to malloc. So I need to remember to have 2 calls to free eventually when I'm freeing up the memory at the end. But that's something I can deal with. All right. The count is just going to be an int, and then the addresses for the left and right children would go here. We're reading the file name and the word for the search term from the command line, so I have argc and argv here. I know it's supposed to be exactly 3 things, so when I run the program, here's what is the way to use it. In fact, we can see this. So if I just say a.out, it tells me, oh, I didn't use it correctly. Give me the name of the program, which is a.out in this case, the name of the file to read, and the term to search for. So if I don't have exactly 3 things, then I didn't use the program correctly. If I have 3 things, I still could have made a mistake in how I used it, but that's more difficult to determine. So I'm going to assume the user is using the program correctly. But if I did run the program correctly and give it the 3 things, here's what the order of those things are. And so argv1 will be the name of the file to read. I'm going to pass that to this function store file to process the file. And then when I get back, I want to search for this term, so I'm going to use this search function to search for argv1 using the binary search tree that was provided. So let's look at store file. So here's my standard stuff for reading a file. I said over here that a file can be stored, or a line of the file can be stored 1,000 bytes, so I'm allocating memory here. And then I'm going to initialize my root pointer to null, because I'm going to use that here in a moment. So once I've opened up the file, then I'm going to get a line of the file, and we need to deal with this situation. What if I have non-alphanumeric characters in addition to spaces? I want to deal with those, so I'm going to clean a line. So I pass the buffer, which contains the current line, to the clean function. Here's that function. So I'll go through it character by character until I hit the end of the line, which is the terminate null. And I say, well, if it's an uppercase character, convert it to lowercase by adding 32 to the ASCII value, because the relationship between uppercase and lowercase characters is a difference of 32. But if it's not a capital letter or uppercase character, then I'm going to come down here and say, if it's not, using the bang, if it's not a match for a digit character, and if it's not a match for a lowercase character, then I'm going to convert it to a space. So instead of trying to store all the possible non-alphanumeric and non-space characters as delimiters, I just convert those things that I don't want to spaces. And then it's easy to tokenize. So that's the logic here. So once I've cleaned up the buffer, now I begin tokenizing. So as long as I'm getting tokens, I want to check and see, is this the very first token I've ever seen for the entire file? If it is, I know that because root is still set to null. And so I'm going to create a node for that. Otherwise, I'm going to use the insert function to figure out where to place the new word. So let's look at add node. So this is very similar to what I did in my videos on binary trees and binary search trees. And if you haven't seen those, you might want to review, because some of this might not make sense. But I allocate memory here for a node and store that in temp. And now I'm going to allocate memory for storing the current token, which I call a word. But all this does is allocate memory. I haven't actually stored the word yet, So then I'm going to copy the token over into that memory location here. This is the first time I've ever seen that token. And so therefore, I'm setting the count equal to 1 and then initializing the left and right children to have null addresses. In terms of insert, this is basically like what I did in my binary search tree video. So let's see what I said over there. So over there I said that the way this commonly works is the binary search tree property I said that the relationship between nodes is basically this. If it has this, is that we'll have some relationship that, say if A is here, and this is just some generic name, it's not the actual relationship, then B is less than or equal to A, and C is greater than A. That's the relationship for building the tree. And then if I have D, that's less than or equal to B, and E is greater than B, and so forth. Now for our particular application, I won't have the equals as part of this relationship because I don't want to store duplicates. So if I actually had, like what we had before, cat, dog, cat, bat, horse, if I still had the equals, then what I would get would be this: cat, dog, cat would come over here if I have equals, bat would be over here, horse would be over here. But since I'm maintaining counts, I want this cat to actually be here and just update the count to 2. So that's why I'm going to deal with, I'll have less thans, greater thans, but equals send you back to whatever the current node is that you're dealing with. So right here I do a string comparison, and I'm comparing, and if there's a match I get back equals, so I just simply update that count. Otherwise I go down the left path looking to see if I can either add a node at the current left child because it's currently set to null. If so, I use add node again. Otherwise I go down the left path by calling insert again, so I'm using recursion. And if it's not equal and it's not down, I shouldn't go down the left path, well then I should go down the right path and make the same types of decisions. Either add a node here because there is no current node as the right child, or go down the right path searching for things. So what do we do now? So when we get back after I built the tree, now I need to search to figure out where to place things. So if we look at search, we have this function, and I want to print the tree because here's what we're really doing. We're printing here. I want to print the tree in sorted order. So because I have the binary search tree property, an in order traversal will automatically print the terms in order. And so this is really the logic for an in order traversal. Go left, use the current node, go right. And so then I use this relationship here, this less than or equal, based upon the relationship between the term I'm using to determine what words to print and whatever the current word is. This will print the things greater than or equal to the search term. But this is still just an in order traversal. And then ultimately when we're done, we need to free up the memory. So for that I use a post order traversal. Go left, go right, and then finally use the current node after I've already dealt with the left and right children. And as I stated when we created the structure definition, we need to remember to free up the memory for the word itself and then free up the node that contained the address of the word. And this was just a function I used for test purposes, so that doesn't really matter. But that's the process. So you have to think about the design, then write the code, and then as I stated at the very beginning, I think that a binary search tree is a good application of this, even if the homework hadn't explicitly required it. If you found videos like this or the other videos that I've created for my C programming course, please hit the subscribe button.